This is lecture 5I, and today we're going to learn how to calculate the heat of a chemical reaction from using standard heat of formations, which are listed on tables that you can look up and use at your convenience. So what is a standard heat of formation? It's the amount of heat given off or absorbed for a formation reaction. So for example, a formation reaction for lithium fluoride would be the reaction that produces 1 mole of lithium fluoride from the elements that compose it in their standard states, which means how they exist at room temperature and room pressure on Earth. So elemental lithium exists as lithium solid, monatomic lithium solid, and fluorine exists as diatomic fluorine gas at room temperature and room pressure on Earth. So the reaction that would need to form 1 mole of the lithium fluoride would be 1 mole of solid lithium plus a half a mole of gaseous diatomic fluorine. So this is a formation reaction. They have hundreds of formation reactions listed on our thermodynamic table on our class website. And instead of writing the reaction out, they just tell you that for lithium fluoride, its standard heat of formation is a specific value, in this case, negative 617 kilojoules. Well, with all those standard heat of formations listed, here's how we're going to wind up using them. The standard enthalpy change for a chemical reaction will always equal the sum of all the standard heat of formations of the products in your chemical reaction minus the sum of all the standard heat of formations of your reactants in the balanced equation. Writing this out in one sentence, the sum of the standard enthalpy of formations of the products minus the sum of the standard enthalpy of formations of the reactants, and then each multiplied by their coefficient in the balanced equation will always equal the standard enthalpy change for a given chemical reaction. And we're going to try a few examples of that today. First one we're going to work on is the standard enthalpy change for the reaction 2NaOH aqueous plus H2SO4 aqueous yields Na2SO4 aqueous plus 2H2O liquid. We could calculate the enthalpy change or the heat given off or absorbed for this reaction experimentally in a calorimeter, but if we want to do it theoretically, we're going to use our standard heat of formations found in our thermodynamic table on our class website. So when you go to that website, to our class website and go to the thermodynamic tables, you'll see there'll be 3 columns in there, something called delta H naught sub F, which stands for the standard heat of formations, and then a couple of other columns, delta G naught sub F and S naught, which are thermodynamic functions we're going to use in Chem 1B. So we're going to only focus in on the column giving us the standard enthalpy of formations. And you'll have to look up each of the reactants or products in your chemical reaction, and then we're going to use those specific numbers multiplied by the specific coefficients in the balanced equation. Starting on the product side, we have sodium sulfate. The coefficient in front of it is a 1, so we're going to multiply 1 mole from the balanced equation of sodium sulfate by its standard heat of formation of negative 1387 kilojoules per mole. The next product is water. There's 2 moles of water, so I'm going to multiply 2 moles multiplied by the standard enthalpy of formation of water found in the table of negative 286 kilojoules per mole. All the products are done. Now we're going to subtract the enthalpy of formations for all of the reactants. So there's 2 moles of sodium hydroxide, so I'm going to subtract 2 moles of sodium hydroxide multiplied by its standard enthalpy of formation of negative 470 kilojoules per mole. And there's also 1 mole of sulfuric acid on the reactant side, so I'm going to subtract 1 mole multiplied by negative 909 kilojoules per mole of sulfuric acid. There's 4 terms here, groups of things that are multiplied, but they're separated by additions or subtractions. In each term, the moles will cancel out. In the first term, moles of sodium sulfate cancel out. In the second term, moles of water cancel out. In the third term, moles of NaOH cancel out. And in the final term, moles of sulfuric acid cancel out. That means each term has the units of kilojoules. So I'm going to go kilojoules plus kilojoules minus kilojoules minus kilojoules. This is a big subtraction problem. So when you do addition or subtraction, because in this case, each of the numbers are going to be accurate to the ones place, my final answer will be written to the ones place. And so if you add up your 4 different values here measured in kilojoules, you'll get a value in kilojoules to the ones place, and I get negative 110 kilojoules. So we would predict theoretically that when this reaction occurs, it's going to release 110 kilojoules of heat energy. And that's based upon the coefficients in the balanced equation. You would write that number to the right of a reaction. So to the right of this reaction, we'd write negative 110 kilojoules. So that's to mean it's negative 110 kilojoules released per 2 moles of sodium hydroxide, or negative 110 kilojoules per 1 mole of sulfuric acid, or negative 110 kilojoules per 1 mole of sodium sulfate, or negative 110 kilojoules per 2 moles of water. This particular reaction is an exchange reaction, which we call an acid-base reaction. It forms water, and these are often called neutralization reactions. So when you calculate how much heat is given off or absorbed in an acid-base reaction, they're often called heat of neutralizations. So the standard enthalpy change for an acid-base reaction is called the standard heat of neutralization. This is something we'll be calculating in experiment 23. Let's try another example. Let's calculate the standard enthalpy change for the reaction 4NH3 gas plus 7O2 gas yields 4NO2 gas plus 6H2O gas. We could do this experimentally in a bomb calorimeter, or we could do it theoretically with standard heat of formations from a thermodynamic table. So I'm going to go to our class website's thermodynamic table, and I'm going to look up the enthalpy of formations for each of the reactants and products, and we're going to do the same thing. If you want to pause this and try to do the calculation on your own, please feel free to. Otherwise, in a couple seconds, we'll go through the calculation here together. Starting on the product side, there are 4 moles of NO2 being produced. So I'm going to go 4 moles multiplied by the standard enthalpy of formation for NO2, which is 34 kilojoules per mole. Then we have 6 moles of water as a product. So I'll go plus 6 moles multiplied by the enthalpy of formation of water, which is negative 242. All the products are done. Go to the reactant side. I'm now going to subtract the enthalpy of formations of the reactants, and in this case there's 4 moles of ammonia, so I'll go minus 4 moles multiplied by the standard enthalpy of formation of ammonia, which is negative 46, and then minus 7 moles multiplied by the standard enthalpy of formation of elemental oxygen. And whenever you have an element that's in its natural state at room temperature and room pressure on Earth, it'll always have a standard enthalpy of formation of 0. In these 4 different terms now, the moles will cancel out. So each of the terms have the units of kilojoules. So I'm going to be adding kilojoules and kilojoules and subtracting kilojoules and subtracting kilojoules. All the numbers in the thermodynamic table are taken to be to the ones place, unless a rare example they've given you something to the tenths place. But they say to assume they're at least all accurate to the ones place. So when I do this giant addition subtraction problem, my answer is going to be able to be written to the ones place. And I wind up getting negative 1132 kilojoules, which is the number you could write alongside the chemical reaction above, which would mean negative 1132 kilojoules per 4 moles of ammonia, or negative 1132 kilojoules per 7 moles of O2, or negative 1132 kilojoules per 4 moles of NO2, or negative 1132 kilojoules per 6 moles of water. Because this reaction that we've dealt with here is a combustion reaction, the amount of heat given off for a combustion reaction is called the standard enthalpy of combustion, or the standard heat of combustion. So we've calculated the standard heat of combustion. Now, if you do it theoretically using standard heat of formations, we always like to present the standard heat of combustion per mole of whatever's combusted. And when you do it theoretically, you're assuming that 4 moles of ammonia are reacting with 7 moles of oxygen. So the heats of combustions that are determined theoretically by standard heat of formations are given as kilojoules per mole of the substance burned. And we're assuming 4 moles of NH3 are burning in this reaction because that's the coefficient in front of the NH3. And in our calculation, we said minus 4 moles of NH3 multiplied by negative 46 kilojoules per mole. So if we want to give the answer to this question, what's the enthalpy change for the reaction in kilojoules per mole of NH3, I would take my negative 1132 kilojoules and I would divide it by the number of moles I used to do my theoretical calculation, which was 4. That's a counted number, so my answer will get to stay 4 significant figures, and I get negative 283.0 kilojoules per mole of NH3. Let's try this. Let's try to calculate the standard heat of combustion for methanol, CH3OH liquid. In A, kilojoules per mole of CH3OH, and B, kilojoules per gram of CH3OH. So we would need to write the combustion reaction to do this. So if we're going to try to find the heat of combustion, a combustion reaction is the substance reacting with oxygen. So it'd be CH3OH plus O2, and you're going to form an oxide of carbon and an oxide of hydrogen, and then that's all, so CO2 plus H2O. Balanced equation would wind up being 2 CH3OH plus 3 O2 yields 2 CO2 plus 4 H2O. If we're going to do this theoretically, we're going to need the thermodynamic data from our thermodynamic table on the class website. So I'll give you that data here. If you want to take a minute and try to calculate the answers to questions A and B ahead of time, you can. Otherwise, we'll follow along and do that in a moment. So starting on the product side, there are 2 moles of CO2 that are being produced. So I'm going to go 2 moles of CO2 multiplied by its standard enthalpy of formation of negative 394 kilojoules per mole. There's 4 moles of water being produced. So I'm going to add 4 moles of water multiplied by water's standard enthalpy of formation of negative 242. Products are done. Go to the reactant side. I'm going to subtract the standard heat of formations of each of the products, each multiplied by their coefficient in the balanced equation. So there's 2 moles of methanol. So I go minus 2 moles multiplied by negative 239 kilojoules per mole. And although it wasn't listed in the table here because oxygen, O2 gas, is in its elemental state and it's in its standard state at room temperature and room pressure on Earth, its standard heat of formation would have to be 0. So often I may not give you that data in a problem. I'll expect you to know that. But theoretically, I would go minus 3 moles multiplied by 0 kilojoules per mole. In our 4 terms, the moles cancel out in each of them. So we're combining kilojoules and kilojoules and kilojoules and kilojoules. Our answer will be in kilojoules. And assuming they're all accurate to the ones place, which the table does, we can, when we do this addition problem, write our answer to the ones place. And I get negative 1278 kilojoules. For A, they want this in kilojoules per mole of methanol. So I did this theoretically based upon an equation in which 2 moles of methanol were being burned. So I'm going to divide that number by 2 moles. And if you divide these out, you're going to have the answer in kilojoules per mole. And that comes out to be negative 639.0 kilojoules per mole. If you want the answer in kilojoules per gram of methanol, then we would just have to switch our answer from kilojoules per mole into kilojoules per gram by using methanol's molar mass. And that's 32.05 grams per mole. I would arrange it such that the moles of the methanol would cancel out. And then I wind up getting my answer in 4 significant figures as negative 19.94 kilojoules per gram of methanol. Now, why does this work? It works because of Hess's law. And so if I can do one example for you to show you why we can just go standard heat of formation of products minus standard heat of formation of reactants, and we always get the enthalpy change for a reaction, we're going to do an example with this reaction, ammonium nitrate decomposing into dinitrogen monoxide and water. And we're going to want to predict what the enthalpy change, standard enthalpy change is for this reaction. And the way we do it theoretically is with standard heat of formations. So you would have to look up in a thermodynamic table the standard heat of formations for all 3 substances in this reaction. So we would look up the standard heat of formation for ammonium nitrate, which is negative 365. We would look up the standard heat of formation of dinitrogen monoxide, which is 82 kilojoules per mole. And we would need to look up the standard heat of formation of water, which is negative 242 kilojoules per mole. Now, what do those values mean? That's the amount of heat given off when you form 1 mole of each of those substances. So for the ammonium nitrate, it's the energy change when you form 1 mole of ammonium nitrate from the elements that make it up, which are nitrogen, hydrogen, and oxygen. And nitrogen is diatomic at room temperature and pressure on Earth as a gas. Hydrogen is diatomic, oxygen is diatomic. So to form 1 mole of the ammonium nitrate, you would need 1 mole of nitrogen, 2 moles of hydrogen to provide the 4 hydrogens in the formula of the product, and then 3/2 moles of diatomic oxygen. For the N2O, the value of 82 kilojoules per mole is the amount of heat that's absorbed when you form 1 mole of NO2 from nitrogen and oxygen. And to balance that equation so that you only form 1 mole of N2O, you would need to have 1 mole of N2 reacting with 1/2 mole of O2. for the heat of formation value for water, that's negative 242 kilojoules per mole. That's the amount of energy released when you form 1 mole of water from hydrogen and oxygen. And to form 1 mole of water, you would need 1 mole of hydrogen and 1/2 mole of oxygen. So if we use Hess's law, we can take those 3 reactions and make them add up to the reaction at the top. We want to have 1 mole of NH4NO3 on the reactant side. Our first formation reaction has NH4NO3, but it's on the product side, so I'm going to have to reverse that reaction. When I reverse the reaction, I change the sign of the delta H. It goes from negative 365 to positive 365. Second, I need to have 1 mole of N2O on the product side, and our second reaction has 1 mole of N2O on the product side. I'll write the second reaction exactly how it's written, and because I didn't change it at all, its delta H value stays 82 kilojoules. I need to get 2 moles of water on the product side. The third formation reaction has water as a product, but it's only 1 mole, so I'm going to have to multiply the third reaction by 2. If I do that, it's twice as much water is being produced. I have to double the delta H value, so I double negative 242 and it becomes negative 484. These 3 reactions should now add up to make the overall reaction at the very top. Let's first cancel out anything that's the same on the left and the right. So the 1 mole of nitrogens cancel out, the 2 moles of hydrogen cancel out, and the 1.5 or 3/2 moles of oxygen cancel out, leaving NH4NO3 yielding N2O plus 2H2O. And by Hess's law, all I have to do is add up my 3 delta H values on the right, and I'm going to get a delta H naught for this particular reaction is negative 34. So we can use Hess's law to do that. How come we can just go products minus reactants? Well, if you look at the product in the reaction, which is the NH4NO3, what did I do to its formation reaction? I reversed it. When you reverse a formation reaction or reverse any reaction, what happens to the sign of the delta H? You change the sign. In other words, you're subtracting it. So anytime you have a reactant, you're going to always have to reverse its formation reaction to get the substance over onto the reactant side. This is why we subtract the heat of formation of reactants. What did we do with the products? We left them exactly how they are. We didn't reverse them, so you don't subtract them, you add them, but if there's a coefficient in the balanced equation, you have to multiply that by that coefficient. So you could actually break down any of the problems we've done earlier today by writing out all of the formation reactions and then using Hess's law, reversing the ones you need to, leaving the ones the same how they were, multiplying by coefficients, and you can make them add up to overall reaction and just add up the delta H's. It always works out that it'll always be reversing the reactants and leaving the products the same. So that's why we say you can use standard heat of formations to calculate an enthalpy change for a reaction by going heat of formation of products minus heat of formation of reactants. Now I want to look at this reaction, aluminum plus iron 3 oxide yielding aluminum oxide plus iron. This is called the thermite reaction, and it's an interesting reaction because it gives off a whole lot of heat and light. I want to show you a little video concerning that.
A metal crucible is filled with iron oxide and aluminum. A small amount of a white mixture of potassium chlorate and sugar is placed on top of the iron oxide aluminum mixture. A few drops of concentrated sulfuric acid are added to the chlorate sugar mixture to start the reaction. The reduction is extremely exothermic and proceeds with a shower of white sparks. The crucible becomes red hot. The aluminum has reduced the iron oxide to iron. When we look into the crucible, we see a ball of white-hot iron glowing at the bottom. When the crucible has cooled, we can remove the iron produced by the reduction of iron oxide and show that it is indeed iron by picking it up with a magnet.
So this is a very exothermic reaction.
The crucible is filled with iron oxide and aluminum.
So it's a very exothermic reaction, has a standard enthalpy change of negative 425 kilojoules per mole of aluminum. If we know the enthalpy change for that reaction, we're going to see if we can calculate the standard enthalpy of formation for aluminum oxide given the standard enthalpy of formation of iron 3 oxide is negative 826 kilojoules per mole. So this is a problem where I've actually given you the delta H of the overall reaction to start the problem. It's negative 425 kilojoules per mole. That's the case. Calculate what the delta H of this reaction is the way it's written, based upon the fact that this reaction is combusting, or not combusting, but reacting 2 moles of aluminum. So we're going to try to calculate the delta H naught of the above reaction from this number, negative 425 kilojoules per mole of aluminum. How do we do that? You just multiply by the number of moles of aluminum that are reacting in the balanced equation at the top, which is 2 moles of aluminum. So if you cancel out the moles of aluminum, you will now know the delta H value you could write alongside that overall reaction at the top of the page. It would be negative 850 kilojoules. So that balanced equation should have a delta H value of negative 850 kilojoules. Now, what can we do with that? Okay, and if I write it over here, just so now it's next to the reaction. For the reaction above, there's a relationship that we've talked about throughout this lecture today, and that is the delta H of the reaction, the negative 850, equals the standard enthalpy of formation of the products minus the standard enthalpy of formation of the reactants. So the delta H value for this reaction, which is negative 850, must equal, follow along, 1 mole multiplied by the standard enthalpy of formation of aluminum oxide plus 2 moles multiplied by the standard enthalpy of formation of elemental iron, go to the reactant side, minus 2 moles multiplied by the standard enthalpy of formation of aluminum, minus 1 mole multiplied by the standard enthalpy of formation of iron 3 oxide. In this relationship that has to be true, I know the delta H naught of the reaction is negative 850. The enthalpy of formation of aluminum oxide, I don't know. That's going to be X. So it's going to be 1 mole multiplied by X. The standard enthalpy of formation of iron is 0. So that's going to be 2 moles multiplied by 0 because it's an element in its standard state. Iron's a solid at room temperature and room pressure on Earth. Minus 2 moles multiplied by the standard enthalpy of formation of elemental aluminum, which is 0. And then minus 1 mole multiplied by the standard enthalpy of formation of iron 3 oxide, which they told us in the problem was negative 826 kilojoules per mole. So same relationship we've worked on throughout this lecture today. It's this now we're not trying to solve for the enthalpy change of the reaction. We're given the enthalpy change of the reaction. You're solving for one of the standard enthalpy of formations. We know all of them except for the one for aluminum oxide. And so this becomes an algebra problem where you solve for X. So I'm going to cancel out the moles in each of the terms. And I'm going to wind up having kilojoules and kilojoules and kilojoules again. So the negative 850 kilojoules will equal 1 mole times X. And I'm going to add the 3 different kilojoules together, 0 minus 0 minus a negative 826. So that comes out positive 826 kilojoules. If I subtract 826 kilojoules from each side of the equation, because I'm doing a subtraction problem, the answer will be accurate to the ones place. So I get negative 1676 kilojoules. Then if I divide by the 1 mole, I will solve for X, which is the standard enthalpy of formation of aluminum oxide. So dividing by the 1 mole, I get negative 1676 kilojoules per mole, and that's going to be the standard enthalpy of formation of aluminum oxide. Let's try one more example like that. Given this reaction, the combustion of octane into carbon dioxide and water, let's say the standard enthalpy of combustion for octane is negative 44.47 kilojoules per gram of octane. Let's see if we can calculate the standard enthalpy of formation of C8H18, which if you actually try to look it up, you may not be able to find it. We'll need to be given a couple of other bits of data from a thermodynamic table, the enthalpy change for the formation of carbon dioxide and water vapor. So I've given them to you here. So if we're trying to find a standard enthalpy of formation, and we know the enthalpy change for an overall balanced chemical equation, I want to figure out first what is the actual enthalpy change that goes along with this reaction, because this reaction is combusting 2 moles of octane. So the delta H naught for the above reaction is going to come from the negative 44.47 kilojoules per gram. I'll need to switch this from kilojoules per gram into kilojoules per mole by using octane's molar mass. So 114.26 grams per mole allows the grams to cancel out. Now it's kilojoules per mole. And if I know how many kilojoules are released per mole, my reaction at the top of the slide is combusting 2 moles of octane. So I'm going to multiply it by the 2 moles. That cancels out the moles. So we now have our enthalpy value in kilojoules that's associated with the reaction at the top of the slide. And to 4 significant figures, that comes out negative 10,160. So if I write that up there, we now have a delta H value associated with this reaction. And now we're going to do the relationship we've dealt with all lecture. The delta H of an overall reaction is always equal to the standard heat of formation of the products minus the standard heat of formation of the reactants. So a relationship for the reaction above is the delta H of the reaction, which will be the negative 10,162. It will equal 16 moles multiplied by the standard enthalpy of formation of CO2 plus 18 moles multiplied by the standard enthalpy of formation of water over to the reactant side minus 2 moles multiplied by the standard enthalpy of formation of octane minus 25 moles multiplied by the standard enthalpy of formation of oxygen. And I know every number in this equation except for one, and the one I don't know is the standard enthalpy of formation of octane, so we're going to solve for that. So the delta H of the combustion reaction is negative 10,160. That'll equal 16 multiplied by negative 394 kilojoules per mole plus 18 multiplied by negative 242 kilojoules per mole minus 2 moles times X, and then minus 25 moles multiplied by the standard enthalpy of formation of an element, which is just 0. So if I cancel out the moles now, I can do the algebra and solve this for X. So moving it up to the top, I'm going to combine the terms on the right side, and I'm going to make them equal to, well, I'm going to multiply them out. It's negative 6,304 plus negative 4,356 minus 2 moles times X, and I'm leaving the 0 off. So combine the two terms that do not have X's in them on the right side of the equation, and that's going to wind up being negative 10,660 kilojoules minus the 2 moles of times X. I'll add 10,660 to both sides, both numbers being accurate to the tens place. So when I do that, my answer will be to the tens place. So 498, or really 500 with 2 significant figures. And to solve for X, divide by the negative 2, and I get negative 249 kilojoules per mole as my value for the standard enthalpy of formation of octane, which really should be rounded to negative 250 to make it a 2 significant figure number.